So then welcome to lecture number 3 in parallel and distributed computing in summertime 2025. So what we are going to talk about today is something more related to performance in general. So this is something that is important for parallel programming, but which you can also apply to serial programming as well. Yeah? And this is, okay, like, let's take as a title for this, the Roofline model. Okay, so what are we concerned with? Yeah, we are concerned with the fact that your computer has not been built for your problem. I mean, in general, this is the case. There are some, I mean, if you do the weather forecasts, then you have a computer that is always doing weather forecast, and this may be a very expensive computer, and this computer may actually have been built exactly for that purpose. But even there, it's very likely that it was made from standard parts, and standard parts have standard properties. Yeah? So in general, your computer is not made for your program. And therefore, it may not fit exactly your purposes. I don't know American English, British English, how many M. So there is a big potential of mismatch between what resources you require and available resources. Now you could say that resources should be, you want to have resources as much as possible and as fast as possible, but this is not necessarily what we mean. What we actually mean is the ratio between different abilities of your machine, yeah, such that their ratio is equivalent to the ratio how you need them. Yeah. Okay. Let's try to understand this. So there's always the available resources. So this is the machine. Available resources. So basically, this is, I need more space. This is the hardware. So say the hardware has a computational power that's usually, if you look at the data sheet of a computer, this will be announced as the peak performance of your processor. Yeah. So I could write P peak, but I now say P computation. So this basically comes from the processor. And this is the number, so I use this hash. The hash operator is always the number of something. Yeah? It's the number of operations per second. Yeah, so it's usually called, is what could say peak performance. So the peak performance is the maximal number of, now we have a little bit in trouble because we're already simplifying here. There are different kinds of operations, and the operations that we mean when we talk about numerical problems, yeah, they are usually related to floating point operations. So you already see that we are a little bit in trouble with the model that we are building, because we are kind of ignoring the non-floating point operations that also take time. Yeah? But say we only care about floating point operations. Of floating point operations per second. Yes.
What will be actually non-floating point operations? I can think of maybe shifting stuff in memory.
Shifting stuff in memory. So there is a lot. I mean, if you look at the, make it very simple. You have a for loop, yeah. So in the for loop, you are increasing an index, or you have to calculate the position in an array. So this may actually be non-trivial. So non-trivial case is you have a finite element. You solve a finite element problem, yeah, and then you have your elements there, and your element needs some information from a neighbor ring element. So then, depending on how you implement this, the coordinate in the memory, so the address in the memory may have to be calculated, or it has to be, we have to read this somewhere, or sometimes we can read it, sometimes we can calculate it. So these things are usually related to addresses, indexes, and so on, and therefore they don't use floating point numbers, they use integers. Yeah? So this is integer operations. Usually if you do a for loop, then you write int I, yeah, equals to 0 to blah, blah, blah. Yeah, so all of these things are then integer operations. So the unit for this is flop. Yeah, we sometimes say floating point operations. So UP, you see, there's a little bit, it's a little bit confusing, because maybe not everybody uses the same notation. Yeah, I read floating point operations where UP, OP for me is still operation. There is sometimes floating point operations per second where the P is for the per, so it's actually the division. So you will read flops, yeah, but I write flop per second, yeah. So this is one thing, you have the processor, yeah, but it's not all up to the processor. You also have to deal with the bus. And here we have a quantity that we call small bs. Okay, doesn't sound so good. This is the bandwidth. And this is the maximal amount of data that can be transferred per time. So we take this in terms of bytes per second. So these are, let me see, now, okay, these are the available resources, and compared to these, we also have the required. By the way, you see we are dealing here with ratios. So with ratios between what is your compute power and what is your traffic power. Yeah, we are not talking about your memory is too small or something. Yeah, so if your memory is too small, then you cannot do the calculation. Yeah, we are assuming memory is large enough for what you want to do. So required resources. The required resources, this depends on your software. So the other one was your hardware, now you're in your software. And here I give a quantity big O. This is the number of floating point operations so I call this here flop, and then I have what I call with this as a kind of volume. This is the amount of data that has to be accessed. And by data access means you have to read it and you have to write it. Both is data access. And from your software, from the operations that you have to do, and from the data that you have to access, arises the so-called arithmetic intensity. So an I will call the arithmetic intensity I. You will find other places where arithmetic intensity is called AI. But I think we are in such an AI hype that it's kind of a little bit confusing to talk so much about AI and meaning something else than artificial intelligence at the moment. So I call this thing I. And the arithmetic intensity is basically so how much work you have for your data, how much work you do on your data. So it's the number of operations that you apply divided by the amount of data that you use. So, and this then has the unit floating point operation per byte. Now you can relate this. So this is obviously your program, yeah. So you have that much data that you have to move around, and you have that many operations that you have to do on them. This is kind of given by your program. I mean, here you may, So if you have an algorithm, this is usually given, but you may modify your algorithm to change this. Yeah? Because depending on what your arithmetic intensity is, you have different different strategies to optimize your code. Because your arithmetic intensity should match the arithmetic intensity of your machine. So what is the arithmetic intensity of your machine? Actually, your machine does not have an arithmetic intensity, but it has a threshold arithmetic intensity that you can define. Which I call now I threshold, and this is the peak performance divided by the memory bandwidth. So you could think about this as kind of ideal, yeah? So because you're using the bus and the processor to its full extent, yeah? So that would use bus and processor to full extent, yeah? So otherwise, one of them would be underperforming. So I can write this briefly down. So the hardware utilization would be optimal in the sense that is optimally balanced. If so this I is not me, but the arithmetic intensity. You see this, somebody bought me this because they thought that this here is a stupid setup, but it's so shaky that my handwriting is getting weird. Matches the threshold arithmetic intensity. So why do we bother? We bother because we have the question, how fast can we actually execute our code? So this is something that PhD students and engineers always care about. So how quickly do I get my result? Yeah. And this is, of course, defined by our limiting factors. Of which we have at least two. Yeah? Namely, we have computation. So we can do, our processor can do it so and so many operations per second. Yeah? So then if we have so and so many operations, it will take at least so and so many seconds. Very obviously, yeah? Here, PC in, as we already said, flop per second. And the other thing is the data transfer time. Because we have a certain amount of data, and if we multiply the arithmetic intensity by the bandwidth of our bus, then this comes into flop divided by byte. So this is the arithmetic intensity times byte divided by second, and you see this has the same unit because this is also a limiting factor for operations. So both of them limit what you can do. And the performance we now call the roof, because it is as fast as you can do, P roof, is then the minimum of your maximum compute power, so your peak performance, and your arithmetic intensity times the bandwidth of your machine. And this can then be made visual with a certain roofline plot. So this is actually the topic of today's lecture. Yeah? So the roofline graph that looks like this. We have, okay, I should make clear from the beginning, this is a log plot. So we have down here, we have the logarithm of okay, I need to be careful here, yeah, because okay, I need to be careful in that sense that when I write log I, then when I write the numbers on the graph, I would also need to have the log of these numbers.
It's a logarithm of a value which is already also logarithm.
And no, okay, so I wanted to indicate that this is a logarithmic scale, but then I should not write log I because then it's not consistent what I wanted to say. Yeah. So just both of them, yeah, both of them are in logarithmic scale. Yeah. So down here we have the intensity. We have the intensity, and up there we have the performance, P. So, yeah. And this is often plotted that it's starting roughly from this center here, and now there is a performance that we cannot cross. Okay, I should have. Okay, let's do it pedagogically in a different way. So there is the peak performance. Yeah. This is a line that you cannot cross. However, there is also this I times BS. That's also, I mean, this is a function that is increasing with computational intensity. This is also something that you cannot cross. So all of this together give you a roof that looks like this. Yeah? So there is a range that's up to a point here. Where you are limited by your bus, yeah, until this particular intensity, and this intensity here is the threshold computational intensity. Up to this, you are limited by the performance of your bus, and above this, you are limited by the performance of your processor. And this point here is called the knee of the plot, and this is where PC is equal to I times BS. So this line here is I times BS. Okay, now what we are interested in is where. So, I mean this knee. So this roof line comes from your machine, yeah, and the performance that you have comes from your program. And what we like to do is to find the dot in this plot where our performance is. Yeah. So this position down here is a function of the computational intensity. The computational intensity is a property of your algorithm, that you can analyze your algorithm and see what is the computational intensity. The performance you can measure, and then what you will notice is that the performance should be below this line, because the line is the upper limit, is the ceiling that you cannot hit. And depending on where you are, you see whether you are in a good range for performing, or whether you're limited by your bus or by your processor. So, and of course the optimal. Am I in black? Yes. So optimal in the sense that you are actually using your hardware, the optimal use of bus. So this is not necessarily saying this is the fastest or otherwise. Okay, optimal in that sense does not mean that it's the fastest code that you could write. Yeah, it is like the optimal use of your hardware. Like if you are far away from the knee, you could do the same work either with a slower bus or with a slower processor. Yeah. So if you are far away from the knee, you over-invested in one of them. That's a bit the idea. And the other thing is, of course, this is the optimistic. So the guy doesn't look very optimistic, but the roof line is the optimistic limit of computational speed, meaning you will never reach it because it is as fast as it could be, so it's the light speed. And the theoretical it's a theoretical limit at least as long as you properly analyze your hardware, yeah, because the reality is a little bit more involved than just these two lines. There are a few more lines that we come to in a minute. So, but before we get there, we look at some examples. Example. Tick. So let's say we have a double S equal to 0, and we have A, which is an array, which I do not now specify in detail. And then we may have something in front here, and then we have say a for loop with int I equal to 0, I is smaller than n, and I plus plus. So these are integer operations that are not inside our model, but that still count. So they will slow our code further down, yeah, and but they are not inside our model. So let's say in this loop, what we do is we use S is equal to S plus A times, so A of I, yeah, in the array times A of I, semicolon, and close. Okay, so how do we get to the arithmetic intensity of this? Obviously, we have to count the number of operations. And these are only the floating point operations now. So how many floating point operations do we have in this example?
It's two. One is an addition and one is a multiplication.
So yeah, in the last line 2, and what does this mean for the entire thing?
It will be, because there's a for loop, it will be repeated according to n, yes, n times.
Okay, so it will be 2n.
Yes.
Yeah, because this here is an operation, and this here is an operation. So, okay, now we have the number of operations. Then we need the number of bytes. So how many bytes do we move? This is a little bit more tricky one. Not sure. So we need to read stuff from the memory, right? So in this operation, we need to read A. Yeah? Now, we are a bit in trouble, and there's a little bit of interpretation that we have to do here. Yeah? Because you could say we need to read A, and we need to read A again. So depending on how stupid your computer is implemented, it is possible that it reads A twice. But modern computers won't do that if things are so close together. So it would read A only once. But depending on the stupidity of your compiler, it could be possible that it reads A twice. And then we would have 2n here instead of n. But I would suggest now that this is n, and because it is double, it is times 8 bytes. So what's about S? See, because S, so in principle, again, your compiler could be stupid and write S to the memory and read it again. So in principle, and that would be terrible, because this would mean once you read S once, and then you write it back immediately again. So in the most stupid compiler would have to read A once, twice, and read S once and write S twice. So the most stupid, the most pessimistic way of interpreting this, and to know exactly, we have to measure, yeah, but the most pessimistic way would be 4n times 8 bytes. Now we assume that the compiler is already clever enough to do this read here in 1 and actually not read this, I mean, only once in a lifetime, in its lifetime, because it is accumulating, it is accumulating on the same thing all the time. Yeah, so it can keep this S in a register. Yeah, so this is the reason why it does not need to read all the time again, because it has a limited amount of registers, yeah, where it can accumulate this S, and doesn't need to write it to the main memory. So our assumption would be here, so we are now optimistic that S is not moved, as it can be kept in a register. But our problem is that these details are not exactly clear. So the compiler could do it in another way, and when the program is more complicated than that, yeah, it will also do this. For example, you have an equation, then A of I pops up twice. Yeah. So if they are close together, they would read it only once, but if the equations get larger and larger and larger, there would be a place when it runs out of registers where it has to read it twice. Yeah? So, and we don't know exactly where this threshold is. Yeah? So, you see, it is already challenging. You cannot necessarily do it all by hand. But this is the way we are assuming it to happen. So because the S can be kept in a register, we assume that this will be just n times 8 bytes. And this here, this is what we called O. And the other one was the thing that we called the volume that we move is this V. So then for our loop, the intensity of this loop is now 2n flop divided by 8n byte. So it's 1/4 flop per byte. So in hardware example, for example, the machine that we use here also for our exercises, Phoenix. Hardware example would be here, PC. is 4 gigaflops, giga floating point operations per second, and the bandwidth is 10 gigabytes per second. So if we put this into our plot, so then the knee, okay, so first of all, what is the knee? So we know we have the knee when the peak performance is equal to the arithmetic intensity of the knee times the bandwidth. So this can be translated in the arithmetic intensity of the knee. The knee is equal to the peak performance by the bandwidth, and this is 4 divided by 10. Okay, it's both in giga, yeah, so we can skip the giga and we get 4 by 10, so 0.4 floating point operations per byte. So this would be where we had our knee, 0.4. So it would look like this. And what we have in our loop is smaller than that. And I'm not trying to do this by scale, yeah, because it's the logarithm, right? So it's not. It is. I don't know here by heart how I draw the logarithm of this, so not by scale, but we know it's below that, yeah. So this here, by the way, is PC. So this has, let me see. So this has a theoretical, let's call it P CO. It has a theoretical maximal performance that is below the performance of the peak performance of our processor, and we can write this as P TO is the minimum of PC and the intensity of the loop times the bandwidth, which is, as we identified, okay, so this is 4 gigabytes per second, and the other one is, okay, so the other one is 10. So the loop was one quarter, yeah? 1/4 flop per byte times 10 gigabytes per second. So I'm running out of space. So this means, okay, 10 divided by 4 is smaller than 4. So this is the P0 is the minimum of 4 and 2.5 gigaflop per second. So this will obviously be 2.5 gigaflop per second. So, and now we see that this algorithm here is memory bound. Memory bound meaning it is not limited by the performance of your processor, how quick this runs. So if you have a faster, meaning if you buy a faster processor with the same bus, you get the same result. So you already over-invested in your processor, but you under-invested in your bus. Yeah? So, okay, one other example. Double A and B, both of them kind of arrays. So say for int I equal to 0, I smaller than n I plus plus. And now we have AI is equal to AI times B, so int is times B I. So what's the number of operations here? Okay, quickly, what is the number of operations?
The first line?
Yeah. In the
multiplication 3, just n.
n. Yeah, so an n, okay, the n flop, yeah? N flops. And the number of bytes transferred, this is again the more tricky one. So how many transfers do we have to do?
Isn't it n as before?
So why you say n?
No. This time is two variables. You're reading A and you're reading B, so
Yeah.
2n.
Okay, why do you say 2n?
So we're reading A.
Yes, this is one transfer, yes. Then we read B, this is another transfer.
Second, yeah.
And then?
So we do the multiplication and we store it again in A.
So we store it again, and what does this do?
Just write it into AI.
So is this a transfer?
It is, okay, yeah, it is because it's writing.
Yeah, so
it's read or write, so.
yeah. I mean, you know, you're counting the reading and you're discarding the writing.
Yeah.
On modern, so you're lucky if both are the same, but usually writing is more expensive than reading. So it is, I mean, it could, so in numbers of transfer, it's 3, yeah? It's 3 times n, so, and now it's double, right? So it has 8 bytes. It has 8 bytes, so the intensity of that loop would be n flop divided by 24, yeah? 24 n sorry. by 24 bytes, so it's obviously 1 over 20. So n usually drops flop per byte. So 24 we have. Another example, for int I is equal to 0, I smaller n, I plus plus. Okay, so if we have ai equals to ai plus b I times s, so it's not easy to see how this is exactly done, because there's some compilers can merge stuff. So in the intensity, now again we have two operations, namely plus and times. So this will be 2n flop the transfer. So because s does not need to be transferred, so because it's always the same. So actually you have to transfer it once, yeah. But compared, if you transfer something once, then compared to something that you have to transfer n times, is not important,
Okay.
yeah.
So that's the reason why in the first example we didn't count like the right interest, because it was a constant.
Yeah, so we are actually concerned within the loop. Then it depends on what you do later. Later again, but with ds, you see, if you put the thing is the following: if you put here something, plus a constant, yeah. So then n does not drop out, but we assume that n. So usually this is only interesting if n is relatively large. Otherwise you don't care about if you do something very, if you have a small problem, then you don't really care about whether it's done fast or not. So the problem is when n is large, yeah? And therefore we discard things that are done only once, usually. Even though they mean you don't really get to the ceiling, yeah? You're always kind of below that. So now moving data, so again it's the same as we had before, 3 times 8 bytes times n. So the intensity here is that twice that of the previous. So it's flop by byte, so it's 1/12. Okay, small change, lots of difference here. So just a reminder, it's not all the same. So for example, if we have things in okay, what did I do here? So if we have okay, this example has strange names for whatever reason. So if they are float, of course you also have to watch out for mixed operations where one is a float and one is a double. That's also possible, that you have to count them accordingly. Yeah, so if you have s is equal to s plus a okay, I made a mistake in my writing here. Yeah, so forget it. So it's it's just, if you do all of that in terms of floats, then this here again is a register. So O would be 2n flop, and V is 1 times 4 because its float has only half of this, and the intensity then would be 1/2 flop per byte, which is the first example just with a different data type. So, as we've already noticed, all of this is using a lot of idealizations. Namely, first of all, we assume that we actually know the number of operations. Well, you could say now we count them, but the problem is by just counting them, you assume that there is no merging or split of operations by the compiler. And actually there would be modern compiler would use merging or splitting up. Another idealization is that we already know what causes memory traffic. So that's the question: when I do an assignment, does it go to a register or stored in memory? So in practice, I find this the most difficult thing that you would use, because depending on how complicated your equations is, you know, the more registers would be used in the computation. So problem is you don't really, it's actually difficult to keep track on how many operations there are, because also you don't see all of them, yeah, and how many in between variables the compiler would be using. And the other thing is you don't actually know how many registers your computer has. So then it's very difficult to know whether it will use a register to keep track of something, yeah, or at what point it will write it back to the memory. So that's difficult to know, unless it is, of course, something you do field operations, yeah, where you do something on the entire field, yeah, where you have to read everything once to memory, and you have to write everything once to memory, but it could also use memory to do something in between. So usually it is uncommon to write something directly back to memory, because you also have cache. So unless you have a very large equation, so yeah, we come to the cache in a minute.
May I ask one question?
Yes.
all of this is decided by the compiler or by the CPU itself? Like where is the stuff, if the stuff goes to register, is a decision of the compiler or does the CPU?
So in C++, you can tell the compiler that you like to, so there is a keyword register. Yeah, but you have to remember that C++ is even older than me. So this keyword is usually ignored. So the compiler thinks it knows better. Different machines have different numbers of registers, and your program is not the only thing that's occupying, your equation that you wrote there is not the only thing that's utilizing your machine. Yeah, it's also how many registers are used for I mean how much of your processors your thread actually gets. Yeah, because they may be split up between different tasks. So, problems that we may have is regarding the exact number of operations generated by the compiler is actually difficult to know. So counting your pluses and minuses is not very accurate. And the reason for this is that processors, at least nowadays, support merged operations. So there are some operations that often come together, and modern hardware may have things implemented that do several things together. And the example for this is that if you multiply so this is a very common operation. You do a multiplication of two numbers and then you add them to something else. Yeah? That's very common. And because it's so common, they immediately implemented this in hardware. So then you have plus. So these are actually two operations, but they are merged in one, so they become one operation. So, and you don't know when it is doing this and when it is not doing that, right? So merging of multiplication and addition. So the compiler may do something else. So for example, your compiler may decide to use your vector, the vector operations. But this is something pretty advanced, and this will only be possible in some cases. But if you optimize, so your compiler may find that, okay, so these operations, I can put in a vector register and do multiples of them in the same time. It's pretty advanced because this is possible only in certain for certain arrangements. Here you would rather ask the compiler explicitly to do it, yeah. So that you have to write your program already in vector format. So, and the other thing that's even more complicated is the exact use of the bus, whether something goes to main memory or does not go to main memory, because you have the thing that's called cache. Cache and prefetches and so on. So at the end of the day, you need to due to the usage, so at the end of the day, you actually have to measure your arithmetic intensity, and it may be different from your theoretical predictions. So now let's draw a little bit more realistic picture of this. Taking a little bit more space. So here we have the intensity, and here we have the performance. And say I define my knee here, and say this comes from the bus, and this here, so worst case, bus and operations in double precision. So, or the largest precision that is implemented on the hardware. Yeah. So obviously we can do operations in single precision, and lots of hardware would do single precision computations faster than double precision computations. Yeah. So say we have a single, maybe other color than that, single peak performance could, for example, be here, meaning now we have two roof lines, yeah, depending on whether you do your operations in single or in double precision. So they would have different needs. So you can increase potentially your roof line according to the peak performance by using single computations rather than double computations. And then there is something else, namely vector operations. They're even faster. So this is AVX on Intel type processors. Yeah. They would increase the roof even more. So all of this here is what your processor can do. But there's also something that you can do to accelerate your bus. So get rid of the bus problem. So the line that is the slope here. So what else could you do?
Write a more performance code?
Yeah, but okay, we'll come to writing more performance codes. No, you cannot change this. You cannot change the roof by writing a more performant code, because this is only hardware. Yeah. So your code will then be a point in this space. Yeah, but not the roof. So what is done is using caches. Yeah. So the line here, because you see, because this is a double logarithmic plot. The slope that you see here is always, because this is a linear thing. It's bandwidth. Bandwidth times computational intensity is the slope is always first order. So whatever cache you have here, you get a line that is parallel to the other line here. That's a property of the double logarithmic plot. Yeah, because the slope of a double logarithmic plot is the exponent in I, and it's always bandwidth times I, so it's always linear, right? So they are all. So if I have a cache here, this line that I draw with the cache is a parallel line to the one that I have here, and then we have different caches. So the one that is the slowest is the L3 cache, and then there may be other caches like, oops, now I'm running out of space here, L2 cache and L1. So of course, okay, I've not, the way I draw this is not optimal. Yeah, so of course this goes on. These things here go on here too, right? So because it's double logarithmic, so this is not zero. Yeah, this is why we can shift this. Okay, so these lines are always parallel.
What's the difference between state L1 and 2 and 3? Is just the speed?
Yeah, mostly the size. And size, yeah, you see the transfer. I mean, here you see that the speed is L1 is fast, L2 is slower, and L3 is slowest, and L3 is usually big. I mean, like, so L3 caches are bigger than the memory that we had when I was.
So, but it's a hardware issue. Like, the bigger the hardware is, the slower is it? Something?
Yeah, usually it is difficult to build something big and quick at the same time. Yeah. Okay, so let's draw this picture again, identifying the different domains where we could actually be. So this is Pi saying, now I draw it like this. Okay, I could. Okay, now assuming that we have only one type of operation, so say this here is the bus, and this is the cache. So I make it a little bit simpler and assume there's only one type of operations, float or double, yeah, and that there's only one type of cache, just to make it a bit simpler. And now saying that this here is the domain. This is one domain that is the compute limited domain. Sorry, I made a mistake. This here this is the bus bandwidth limited domain, and in orange we have the cache bandwidth limited domain. So now, depending where you are, you will try to do different things to optimize your code. Say, okay, let's write this down. Only texts. Depending on the limiting factor of the program, or the program's performance, different optimization strategies would be effective. So one thing I don't want to talk about now a lot is, first of all, if you have your program has a certain intensity, right? So you know where you are on this intensity axis, and then you can measure your performance, and then you will certainly see that you are below the roof, yeah. But if you are below the roof, so first of all you have to optimize somehow the structure of your program. I mean, you will always be below the roof, but there's an acceptable amount of being below the roof and an unacceptable amount of you're being below the roof. So you always try to get close to the roof first, yeah? But then, and here, if you're getting in this red range, you can actually change. If you get closer to the roof, you can actually change your limiting factor potentially also, because you can get out of the one range to the other range, yeah? But this is not what I want to talk about. I want to talk about, suppose you're already close enough to the roof. What can you still do to optimize things, and what don't you don't need to optimize? So in these three regions, if you are bandwidth limited, so bandwidth, so say bus, so this is the red one. Okay, I didn't begin with the one. Stupid. Okay, I'll do it this way. If we are bandwidth limited, you have not used the arithmetic compute power and cache speed so they cannot be fully utilized. So here you would try to optimize first to better utilize your cache. No, sorry. I mean, yes, you would try. Okay, so what I just said was could potentially be misunderstood. So you are limited by your bus, yeah. So what you would try to do is to use your bus less, and you use your bus less if you make your program being better in using its cache. I mean, reusing data more often, yeah, less using the bus. So more cache use, if this is possible. So in this way, if you try to if you try to reduce your amount of floating point operations, it wouldn't help you if you're in that limit. Yeah. But you have to think about better organization of your data, because this is what limits you. So the way this can be done is you try to increase the locality of your data. So this can be done in different ways in a parallel and in serial programs. So in serial program, you try to reuse data as often as possible before processing new data. So the idea is that everything that you do with the same data, you better do at once. Yeah? And keep this in a small area and then go on to another area. That is a way for optimization. And in parallel program, this is kind of similar. So try to use data from a close, so meaning as small as possible. Yeah, so don't distribute the data that you need from very far away on the same process. So by splitting up your problem in different parts, try to give each of the parts a very local amount of data. Yeah? So if you are cache limited, so meaning that your cache is utilized a lot, this is already not too bad because you're no longer limited by your bus. But the compute power is not. So then the only thing that helps is try to reduce the overall access to memory. So this basically means increase the computational intensity by lowering traffic. And if you are compute limited, and now I'm time limited because we said that we wanted to stop at 11:15, and this is what we have now. If you are compute limited, then you have too many operations that you have to do, so you are limited by your processor. So you're using the compute power very well. But the bus and the cache not fully used. So what you do then, you optimize your equations and trying to reduce operations. So this is something that maybe the most obvious thing that you would think you should always do, but in reality, simplifying your equations, doing less computations, is not always helping you. It's only helping you if you're really compute bound. Yeah? So, and in this way, you want to reduce computational intensity. See, there's sometimes you want to increase computational intensity when you're memory or cache bound, and in the case where you are compute bound, you want to reduce computational intensity for optimization. But it is important the way how you do it. Yeah, in one you don't want to if you are limited by the cache, you don't want to increase computational intensity by making more calculations. You want to increase it by doing less traffic. Yeah, and here in this case, when you have too much intensity because you are compute bound, you want to reduce the number of operations that you do. Well, reduce computational intensity by reducing, I'm never finishing my sentences, by reducing the number of operations. And if possible, use parallelization. So for example, inside your processor there will be that usually has a vector unit. So you can, if possible, use vectorization. This is useful if you are compute bound. If you are not compute bound, then using vector operations doesn't help you anything. Okay, sorry for now. Anyway, taking over time, I will stop the YouTube recording now.